Hello everyone, so I'm Théo Galifajou and I'm very happy to present my recent work on multi-class Gaussian process classification, which is a joint work with Florian Wenzel, present here, Christian Donner and Manfred Upper from the Technical University of Berlin. So what do I mean by multi-class classification? Well, let's take an example. For instance, you want to predict what type of cancer a patient might have from a series of features that you collected on him. Well, there's a few things you want to do. Let's say you want to predict the type of cancer you might have, so it's a typical multi-class problem. Well, there's a few things you want to have. First, you want calibrated probabilities. So if you say that there is 70% that this patient has cancer type 2, this should be 70% and not something arbitrary. Another thing you want is uncertainties about your prediction. So if your patient is a complete outlier from your training data, you want to know that, and you want your model to tell you, my prediction doesn't make any sense, you should not trust what I'm predicting. And finally, a good bonus would be to have fast training and prediction capabilities, as well as being able to train on large amount of data. So to achieve this, and more particularly the uncertainty part, we're using Gaussian processes, as you could guess from the title. So what are Gaussian processes? Well, they are stochastic processes. When you take any collection of variables from this process, the joint distribution is going to be Gaussian. What it means in practice and how we use them in machine learning is that we put a Gaussian prior, multivariate Gaussian prior, over the realization of a function on these data points. And I will not go into details on how Gaussian processes work. Probably a lot of you know this, but basically we just want to fit a function. And they have many desirable properties. First, it's a fully Bayesian approach. So we're going to get a posterior is going to have a distribution, and we can then have uncertainties about our predictive likelihoods. It's very flexible. These Gaussian processes are non-parametric, so it means that we just depend on the kernel that we're going to use for our Gaussian process to dictate how it's going to behave. And finally, Gaussian processes are quite a large field, and there's a lot of optimization techniques that allows us to go always a bit forward and be more efficient. So they're a nice framework tool. So what is my model actually? Well, we have some data. Say we have n samples in X, and for each sample we have a label Y, which is one of k possible classes. So now, that would be the basic thing. What we introduce is this latent Gaussian process, so latent functions, f, and we have one per class. And what we do is that we're going to train each of this latent and then merge them via a likelihood distribution. So we just train each latent separately, merge them, and then we got our prediction. So what about the likelihood now? Well, there are many possible choices, of course, and there are already been a few in the Gaussian process world. The first one is, of course, softmax, the most known in the machine learning community. And to show you the effect of each of this likelihood, I'm showing a toy data set where we have data coming from 3 multivariate Gaussians. And you might see that there is quite some overlapping in between these different multivariate. So it's kind of a hard problem, and this is what I want to show you here, is that there's another likelihood called robustmax, which is, as its name indicates, very robust to outliers. But then a counterpart is that you get very, very sharp decision boundaries. So if you compare to softmax, you have some kind of gradient in the likelihood between the different classes, where robustmax is just 1 or 0, basically. Another recent likelihood use was Heaviside. So the idea is that you just take the largest latent Gaussian process for your prediction, and then because you have some you have a variance on your latent, you actually have some gradient between the classes. But finally, I would like to introduce to you a new likelihood called logistic softmax, which is basically softmax but with a logistic function. And this basically respects the same properties than softmax, except of some small differences. So how about we quantify? Because now we can see that robust max has definitely a problem because it will not take into account that one point might just be, it does not give proper likelihoods for all points. And to quantify this, you can look at the accuracy versus the confidence. So just imagine that you take, you make your predicted likelihoods and you get points with 0.3. You would expect to get 30% accuracy on these points, right, in an empirical manner. Well, what you can see is that most of the likelihoods work pretty well on this. The ideal is red lines here. But robust max tend to completely ignore the regions between 0.1 and 0.9. It's just going to go 0 or 1. So this is not really adapted for our case. So what did we want? We want good uncertainty calibration and fast and stable convergence. So for the calibration, we actually get something which is working pretty nicely. Now, how about the inference? Well, what we propose is to transform this likelihood, and that's why we have this special formula, and to obtain conjugacy via augmentation. What do I mean by augmentation? Let's imagine you have some marginal, P of x, and you actually know that you can write this marginal into a more simple form, in a simpler form, P of x given y, P of y, and this form is much easier to compute. But now you get the problem of the integral. Well, we can just simply take the joint distribution of x and y, which basically means that we add y to our model. And it might be, the inference might be much easier if we optimize x and y together than just x. And that's what we're going to do repeatedly. So now I'm going to go in a bit of technical part, but I think I learned a lot of stuff on this part, and I think I wanted to share them with you because they're quite interesting. So here you have a graphical model on the top right, top left, and I'm going to update what variables we have given my augmentations. So the first, I would like to introduce you a good old identity from Analysis 101, which is 1 over x is the integral of exponential minus lambda x from 0 to infinity. So we're just going to use this identity and replace our fraction by this integral. So now we have this integral, which is, of course, a bit intractable, so we just remove it by adding lambda to our model. So that's my augmentation strategy. Now, why did we use logistics of max and not softmax? Well, for the next step, we're actually going to need sigma to be bounded, so this transformation to be bounded. And sigma being bounded by 1, we can just rewrite sigma of x by 1 minus sigma of minus x. So I simply replace it here. And people who are familiar with the Poisson distribution might recognize this is the moment generating function of a Poisson distribution. And we can simply use this and replace my exponential by this series form. So if you remember, moment generating function is the expectation of the exponential of t. And here, exponential of t is simply sigma of minus f. So we replace it. And a series is nothing but some kind of integral, so we can just simply add n to our model to get rid of the sum. So now we have a much simpler model because everything is a product, and we kind of like products in Bayesian inference. So we just have one last step because the sigmoid is still something which is not conjugate. But now we come to quite classic, a very nice trick called the polygamma augmentation, which is basically telling you that the sigma to the power of n is a scale mixture of Gaussian. So here the exponential part is simply a Gaussian in x, and then it's scaled by a polygamma distribution, which is a bit complicated distribution, but we have nice properties like knowing the moments, and we can sample from it. So we just, again, apply this identity, and it looks a bit complicated, and I passed the sigma of fi in the product by using the delta Dirac function. You can find more details on the paper. But now I'm just, again, going to remove the integral by adding omega to my model. And now we have our final form. So if you're completely lost in the past few slides, here is what it looks like. So we have, instead of logistics softmax, we now have a product over Gaussian likelihood over f. And we have now a complete graphical model with additional variable that we're going to optimize as well during our training. So the nice thing about it is this is Gaussian, so we really reach our goal. And now for optimization purposes, we actually add sparsity. So by sparsity, I mean to add inducing points in the TTS manner. And what do we do this is because if you know about Gaussian processes, their training complexity is about O of n cubed, where n is the number of data points. And by using inducing points, we have a complexity of m cubed, where m is the number of inducing points. So now we reach our goal. We have something which is conjugate. And now, how do we do inference about it? Well, now we're in the sweet, sweet land of conjugacy, and everything is nice and beautiful. So we have closed form full conditionals. And this is quite an ideal thing to have, because first thing you can do is, of course, exact Gibbs sampling algorithm. And this is, to our knowledge, like the easiest exact sampling for multi-class Gaussian process classification. And you can also, of course, do variational inference, which is more scalable with a number of data points. And here we use a structured midfield approach. And note that n and omega are naturally coupled already from the form of the conditionals. What does that mean is, since we have the closed form full conditionals and we use this variational inference technique, we actually have a block coordinate ascent algorithm. So it's very related to what Matthew Johnson talked about yesterday, that you just literally update your parameters by their optimal value, and you get these natural gradient updates. So what does it mean in practice? Well, you have a very stable algorithm because you just update your parameter, especially the covariance matrix, by updates that will keep this positive definiteness. Well, if you use variational inference like vanilla variational inference, you might have to do some tricks to actually keep this positive definiteness. It's convex, so the elbow is convex in F, which means that we have only one global optima, which is quite a desirable property. And it's fast, it's really fast. So if you fixed hyperparameters, you converge in maybe 5-6 iterations. So now you might wonder, okay, but you added all these parameters. Doesn't your model actually lose accuracy or lose something because you don't have any free lunch like this? Well, we wanted to quantify this, and to do this, we are comparing what we call the truth by sampling via our Gibbs sampling algorithm. And we're comparing to vanilla VI, which is the top row, and our augmentation technique. So what is plotted here is the predictive likelihood, P, the predictive mean, and the predictive variance. And we do this for a test set, and we here plot all the points. So what you see is that first, the variational inference and the augmented variational inference look pretty much the same. We have, as expected with variational inference, a lower variance than the truth, but it doesn't seem to impact much the likelihood in the end. So we can say that we're actually pretty close to the truth, even with augmentation. And please note that all this augmentation are not an approximation. So it means that if you marginalize out, again, all the local variables that we added so far, you would actually recover the exact likelihood. Now, how about convergence? Well, we compared to two state-of-the-art methods. The first one in orange is using robustmax and is relying on stochastic variational inference with natural gradients. So it's a very efficient method already. And it's using robustmax. So as we saw, it's like not so good for uncertainties, but it's the most efficient method in terms of variational inference that we found. And the second thing is in green, stochastic expectation propagation, which is using Heaviside. And yeah. So what we plot here is the training time. So note that this is in log scale. And against the log likelihood of a test set, the negative test log likelihood, and the test error. And what you see, so we are in blue, that actually the convergence happened in terms of seconds on the MNIST dataset here. And then there's actually a slow convergence, which is actually due to the hyperparameter optimization, which actually takes most of the time. The orange curve here has a lot of trouble, and actually this is one of the nicest plots because it tends to be very unstable. Since you have no guarantee about this positive definiteness, you get sometimes very unstable results. And on the other hand, EP tends to be much slower, but converge pretty well as well. So in conclusion, I presented to you an efficient and stable algorithm by using augmentation. So just an idea of like, if you have some problem with something which is intractable, you can actually transform it by adding more context to make it more tractable. We managed to have good uncertainty calibration even though we're using variational inference. This is efficient in the sense that we can actually train with millions of data points quite easily. And if you want to check it out, there's a code available in a package, augmented Gaussian processes.jl. So this is Julia code, but this is of course usable from Python as well. Thank you for your attention.